Yeah, thanks again, everybody, for joining us here today for this webinar on data transfer. And my name is Marty Kandes. I work in the high performance user services group here at SDSC. We're sort of the customer service, desk for any of you that might be using one of the NSF funded supercomputing resources we have here at SDSC. So if you have any follow-up questions while you're using any of our systems, we're the team that you'll be probably contacting when you reach out to ask any questions. Today's webinar is on data transfer, is part of this new program we have called Complex, and my co-PIs Bob Singovitz and Nicole Walter are here to help answer any questions as we go along today. The idea for the idea of the complex training program is really to create a set of educational resources and webinars, tutorials for the NSF cyber infrastructure community to help train end users of these complex systems about the key concepts and skills that you need to effectively utilize them for your research. And we're really trying to focus on sort of these core non-programming skills. Many of the users on these systems that we help support and run and that you might use for your research are not necessarily writing their own code, creating highly complex parallel applications themselves, but they're using other community codes that are developed by other teams around the world and are simply used as part of your research workflow. And so the idea of the Complex project is to target the educational material that we're creating for that use case, where if you are not someone who's writing your own code, you're just using software out there in the world to help you do your research. We want to help you understand the different concepts and skills that you need to use that software on advanced high performance computing systems like we have. Our major one in SDSC is Expanse right now, and this is the idea of the Complex project. Today's talk is the first of what I'm probably going to put together into a three-part series for topics on data management, right? So data management is a very important part of any sort of scientific research workflow, whether you're actually collecting data from the lab and analyzing it, or running simulations to, model some sort of physical process in the real world. Data transfer, data management, understanding how to use these different storage systems that are available to you on these advanced computing resources is an important skill to learn. And the different concepts associated with it are important to learn how to use them effectively. And so today is the first talk in this sort of series of three that I think we'll eventually get to. And it's really focused on how to get your data from wherever it's located now to an HPC system so you can use it for analysis, or whether you're running simulations, how to get the data back to some backup system or whatnot. And the different types of tools and concepts that you'll run up against that will help you sort of create that sort of research workflow in an organized and efficient sort of manner. But one disclaimer about today's talk and the sort of complex series in general is, some of these topics like data management are huge fields of studies in themselves, and we're in Complex. It's really focused on introducing you to sort of the minimal set of tools and concepts that will get you started in any given area that we're presenting, right? And so for these data management topics, really talking about sort of these core skills of like, what are the storage resources that are available, what are the types of file systems, what tool do you use to transfer data from this system to the other? So it's very straightforward, hopefully, and it doesn't get too complex. But there's a whole world of other sort of things about managing data and data use agreements and things like that that aren't going to be covered here. It's really about sort of the nuts and bolts day-to-day interacting with your data on HPC systems. So for today's, the goal I have for today is to cover sort of a survey of different tools that if you're not familiar with them, you might want to learn more about them and incorporate them into your workflows when working with HPC systems. And this is sort of the rough breakdown of what that's going to look like. So we're going to look at some tools about how to sort of just get data from that might be available on the internet that you want to download and use in part of some analysis, or maybe you're training some deep learning model and there's some standard data set out there that everybody uses. You can understand some of the tools that you would use to grab that data from the internet and bring it into the system that you want. We'll also talk about data integrity. If you're not familiar with that, we'll cover what that means and how to check that. We'll talk a little bit about data compression. So when you're transferring data from point A to point B, sometimes you want to shrink the size of that data to reduce the amount of network resources that are required. And we'll touch a little bit on also the types of data storage and file systems that you'll encounter on HPC systems that we have. I'll cover sort of the major 3 or 4 that we have available on a system like we have at SDSC and on Expanse. And then we'll also talk about sort of a survey of sort of the key data transfer tools that you'll actually want to think about using depending on the different situations you might find yourself in, depending on how much data you have versus the format it might be in and so forth. Anyway, so that's sort of the outline for today. The one thing another disclaimer I just want to give for not only this talk, but a lot of the complex talks in general is, high performance computing systems and supercomputers, basically run on Linux. So for most of the program, right, we're trying to highlight the standard command line tools you'll find in Linux or Unix-like environments. So if you're don't use Linux daily on your personal computer, you might have a Mac, which is a Unix-like operating system, and you have a lot of the same tools built in. If you're more of a Windows user, there are different Windows applications and things that do similar types of or used for similar types of applications. But one of the things that I usually try to recommend for Windows users, if you're not familiar with Linux environments in sort of a day-to-day basis, one way to really start learning that is through the Windows subsystem for Linux. So you can sort of get almost native Linux environment on your Windows machines today. So that's sort of, if you're looking to sort of practice your Linux skills, that's definitely what I would recommend checking out. Okay. So let me just check my time. Okay, so what is data transfer, right? So usually when we talk about data transfer in the context of scientific and high performance computing and research in general, what we're really talking about usually is file transfer, right? So all of our data lives on computer systems in files in some form or another, in some sort of formats, and we're typically trying to move them from one source system to one destination system, right? So we have one data sitting on one storage server, we want to get to another, and for whatever reason, whether it's to back up that data, to move it to an advanced HPC system, to do some more heavy number crunching on the data that we have. This is the key problem, right? That we need to move one file or many files from one place to another. How that data is organized and what format it's in will matter, and how much data you have that you're trying to move from one place to another will matter, right? So these are sort of the key components and questions that come to mind anytime you want to transfer data, right? And so when we also talk about, people throw around the term data transfer, sometimes it's also used sort of as an individual reference to an individual instance of a file transfer, right? So these are the questions that you have anytime that you want to, instantiate a file transfer from one system to another, right? These are the questions that you always want to keep in the back of your mind. Okay. Now, I had a little bit of trouble trying to figure out how to break all this down and the different types of tools that you might want to use to get data from one place to another. But this is sort of how the table of contents for today's talk will break down. So as I mentioned, we're going to talk about a few tools for downloading data from the internet. So sort of just someone else has posted the data somewhere else that you can essentially get a URL to and pull that data into the system wherever you want, whether it's your personal laptop or whether it's in an HPC system. These tools, while not all of them will always be available, I'm going to cover the most common ones and usually a few tools that are, a little bit more specialized and maybe you haven't heard of before that you might want to check out. So, but yeah, so let's go ahead and get started. We have a very limited amount of time for these webinars. So they are really more of a survey to introduce you to the different concepts and tools that are available. Eventually we're hoping to have some tutorials so you can work through the material yourself and run some examples, but today we won't have time for that. But at the end of the talk, at the top of the hour, we will have I think as Susan mentioned, a 30-minute question and answer session where we can talk a little bit more about questions you have about any given tools or different things that I don't cover. Or even maybe we can, show some examples if people are interested. So we'll if you're interested in that, please stick around the Q&A session after the talk. Okay. So downloading data from the internet. So this is sort of, I think, the easiest thing to, start with, and some of the tools that if you haven't used them before, that I use quite a bit. This is probably one of the most common tools that I use myself in my day-to-day work. I'm always sort of needing to download things from one place or another and get them onto a system like Expanse or onto my personal laptop here at home. But so this tool wget is what's known as a non-interactive network downloader. But essentially what it does is if you've provided a URL, it will download that URL contents to the system where you run the wget command, right? And this is a very common tool. It should be available in any Linux distribution that you interact with on any HPC system, or I would, even the Windows subsystem for Linux, I assume the default, probably Ubuntu OS that they install there for the standard installation has it available there. So this is one of the most common tools you'll find just installed by default on any operating system. It's probably in Mac OS as well, right? So but it's very simple, and these are 3 commands here that show its basic usage, right? So you can download a single file, a URL, or a single URL. Here, I'm targeting a data set that I use as sort of an example of this image data set that was created for sort of studying machine learning algorithms, especially computer vision. So the one thing to keep in mind about wget, it's sort of what we would call a single stream download. So it's not a multi-threaded application. So it is limited to sort of a single CPU core or single network connection download. So it's not the fastest thing in the world, but it's very robust, very reliable, and it has some nice features. Like if you want to create a list of URLs that you want to download, you can put those into a file, as I've shown here, and download multiple files, right? So if you just want to queue up a whole list of files that are stored somewhere that you want to download, you can just throw those into a text file, set wget to download it, and they will start downloading those files. The other nice thing is, that if people have played around with some download tools or some data transfer tools, not every data transfer tool actually does a good job at resuming downloads, but that is also one feature that's nice about wget, that you can resume a large download. So this example here is a very large data set. It's about 138 gigabytes. It's going to take a while to download if you try to run it. But you can always resume the download where it left off with wget, which is really nice. Another very common tool that you'll see used in examples or tutorials or documentation that you might come across is the curl command line tool. This is a very sophisticated communication tool. It's not only a tool for downloading, that's usually what you'll see it used for in the simplest cases. If you come across this in some sort of documentation, but it can do outbound request. It can do all sorts of network protocol type requests. I don't even know how many types of network protocols it supports. It's a lot. It's a very sophisticated tool that can do many different things. But the simplest thing it can do, you can definitely download files just like you do with wget if you prefer curl. It's also not multi-threaded, so it is also limited to sort of a single. It's a single connection per file. So it's not the fastest thing in the world, but it is also, again, like wget, very robust, definitely up to date, always under active development. And it's a standard tool that you'll see out there being used for downloading data. Right? It's not my preferred one just because it's overkill, I think, for that thing. That's why I use wget. It's like really simple. It has basically the same features that I need. One of the interesting ones here is I do have this last command here at the bottom here is that you can, unlike wget, right, which you can sort of queue up a list of files to download. One thing that's kind of interesting about curl, you can actually download multiple files in parallel. So it'll actually spin up multiple connections to different files and download them in parallel. So if you do have a large list and want to increase your throughput, curl is one of the ones that has a little bit more fancy features like this that allow you to get the data you need pulled down from the internet to the system where you want it a bit faster. One that's a bit more unique that you don't see a lot installed by default is this ARIA 2 download utility. But it's quite nice in the sense that it's very similar in its sort of robustness and simplicity to wget. And so this is one tool you'll find that we do have actually installed on Expanse. I don't know how many other systems on the NSF sort of roster have it, but if you are looking for a downloader that has parallel capabilities with parallel connections per host, this is the tool that you might want to try, right? So this actually has multi-threaded, multi-connection per host downloads. You can actually even point, if you know that the file that you're trying to download is actually hosted across multiple servers, you can actually point the tool at all of the URLs that are the same file, and it'll pull from multiple hosts, right? So it's not only can you use sort of the say if you have like a multi-core, processor in your laptop and have multiple connections, network connections from your laptop, you can actually point it to different multiple hosts out on the internet, right? So which is kind of, just a little bit more fancier than wget, but you don't see it as common, right? So those are sort of, the spectrum of sort of download tools if you're getting started with looking at different tools to just download a bunch of data from the internet. These are the three that sort of I'm recommending here. Okay, now the reason I start with this, simple examples of just downloading URLs, files from the internet is one of the concepts that people don't think about a lot usually, but should maybe more so in especially since we're trying to do scientific research and reproducibility is the concepts of data integrity and checksums. So I don't see. Maybe some people here do use checksums in their work all the time, but if not, this is one topic I thought was important to include here in these tools here. So we'll talk about what that is. So data integrity. So data integrity is very simple. It's the idea of like how do you preserve your data that you have and make sure it's consistent over time. So it's basically, how do you prevent data corruption, right? So that's what data integrity is trying to preserve, right? So prevent data corruption, right? But when we're, say, downloading random files from the internet, how do you know that the data that you've downloaded was not corrupted in transit, right? As you're transferring the data from the remote host to your local system where you want it, right? And that's the question of checksums, right? So there's this URL here pointing to this CFAR data set that I was using in the download examples. You can definitely visit it. And I'll show you here in a second what you'll see there is you'll see a list of checksums for the files that I was using in those examples to download. So what is a checksum? So a checksum is simply a block of data that is derived from a larger block of data, right? So let's just replace. It's almost like a unique fingerprint or ID for a piece of data, or in this case, a file, right? So if we feed a file and its contents into what's known as a checksum function, the output of that function is that ID or fingerprint that is hopefully unique to the input that you provided, right? So it's a way for you to digest this information from this file that you have and provide a easily referenceable value that people can look up, essentially, right? That you can, if you took the file that was, say, on the remote host and someone ran the checksum there, and then you download the file and you run the checksum on the file on your local host, that checksum, that ID, that fingerprint on both ends should be the same. Otherwise, something is different, right? That's the idea, right? So you have this way to verify that the data that you received on your end is the same that was published from, say, the server, right? So this is used a lot. You'll see if you do any work, and especially downloading your own software and installing things in on your system, right? A lot of software that's deployed, right? That you'll find these checksums associated with that version of the source code, right? Because if the checksum that you have is different than the official one that was published, right, then there might be something fishy going on with the source code version that you have, right? Or you just have a corrupted piece of source code. Anyway, so that's what a checksum is. It's this unique fingerprint or ID for an individual file, essentially, right? So how do you compute a checksum? Well, there's, as I mentioned, there's something called a checksum function, right? So there's different algorithms and functions that produce different types of checksums, right? And so the two most popular I'll cover here are the MD5 hash or checksum. So the output of a checksum algorithm or checksum function is usually, colloquially called to as a hash, right? So if you go to that CFAR 10 website, you'll scroll down and look at sort of these links that I was downloading in those examples. And the author there provides the checksum, the MD5 checksum or hash value for each individual file format of the data set that they're providing, right? So once you download those files with one of those tools to the system you want it at, you can then verify that you have received the data as expected, right? By running, in this case, this MD5 sum tool will calculate the MD5 hash value, and you can compare it with the one that the author has published on their website, right? So this is one way to provide this basic data integrity between a data set that you want to use for your research as you move these data sets around from systems to systems, right? Right, because if you don't have this data consistency, this integrity across systems where you might be running the analysis, you might have access to multiple HPC systems where you're running the analysis, right? If the data set is corrupted at one, the results of your analysis might be different at one place versus the other, and that would, probably cause a lot of hours of trying to figure out what went wrong, maybe, yeah, depending on your workflow. So this is probably the most common hash value that you'll see or checksum used, just because it's sort of it was the most popular one for many years. However, it's sort of deemed to be not secure. It's, there's all sorts of cryptographic sort of reasons for, what makes a secure hash algorithm. It's essentially usually comes down to how many collisions you can find between, different inputs and outputs. Anyway, but so the one that is a little bit more expensive to compute is this SHA-256 checksum. But this is probably the second most and the industry recommended standard hash that you would usually provide to publish, what if you wanted to associate a checksum with, some data that you're publishing, this would be definitely one that you would want to include in addition to the MD5. The MD5 is a little bit easier to compute, a little bit quicker than the SHA-256, but this is the one that sort of, you'll also see side by side, usually published with an MD5 checksum, in case people want this one instead. And just these tools, this SHA-256 sum command line tool and the MD5 sum command line tool, these are standard tools again that you'll find installed on every operating Linux, Unix-like operating system that you'll interact with. They're just kind of standard tools that will be available. And the one thing that I will note for Mac OS users is, I don't know the reason for this, but their SHA-256 and MD5 sum tools don't include the sum part at the end of the name. So you'll type in just SHA-256 and the file name versus on a Linux or any other sort of Unix-y operating system, the command line tool is named, with this sum at the end. So, okay. So that's what checksums and data integrity is good for. Another obvious area that's important when transferring data is data compression, and maybe less so data archives. And so, obviously we'll cover a few of these tools here. Obviously, I think most people probably have a decent concept of data compression, but the idea is just to reduce the amount of data that you have to send over the network before you transfer the data, or if you want to reduce the amount of storage on each end that the data utilizes, right, is another obvious reason to use data compression. If you're not familiar with data compression, but there's different types of data compression algorithms, and the different tools that you might encounter or the type of data that you're working with will usually have an impact on what type of data compression algorithms that you're using. So there's essentially two broad classes. There's lossless compression techniques and lossy compression techniques. And hopefully it's pretty obvious, but lossless compression techniques are essentially algorithms that allow you to reduce the size of your data in a particular format such that it can be reconstructed without any information loss when you decompress, say, the file, right? Lossy compression techniques are able to achieve usually much higher compression, what we call compression ratios. So how much you're able to shrink a file or a piece of data with the algorithms, but they do so at the cost of actually throwing away sort of information that is deemed less important by whatever compression algorithm is being used. And one of the compression algorithms that you can kind of get that you probably have maybe a natural feeling for is with digital images, right? And so things like JPEGs. This is a image of a cat here, a JPEG image that is showing the quality of the image as you move left to right or right to left versus the compression ratio that you're using to compress the data that's in the image. So sort of every vertical stripe is changing the amount of compression that's implied to the image itself. So you can see as you increase the compression ratio applied with this lossy algorithm, the details of the cat image are degraded, right? But for whatever for whatever type of application you might be using, whatever type of data format, there's reasons that you might want to use lossy compression versus lossless compression, but this is kind of the two broad class of techniques that you need to be aware of, because the types of tools you might use will implement one or the other types of algorithms, or sometimes they're used in combination even, depending on what you're doing. But where you run into compression usually, working sort of with command line tools in Linux, is with gzip. So there's a lot of files out there, which we call, well, I guess that's the next slide. Anyway, so let me focus on this. So gzip is sort of the most commonly used compression tool that people will use when they start working in a sort of a Linux environment or Unix-like operating system. I didn't check if Mac has gzip installed by default. It may not. I don't know. I have to go back and check. It might just have zip, but that's a different story. But essentially, this is just a file format and compression tool for that uses one of these lossless compression algorithms. So you don't necessarily get high compression ratio, so you don't save as much space as you would if there was some sort of data set where you could use a lossy compression technique. But most of the time when you weren't interacting with files on computing systems, we're usually wanting to use lossless compression techniques, right? Obviously, if you're, say, compressing like source code or some sort of text, you don't necessarily want to throw away information in those types of data sets, right? It's really lossy compression techniques you'll usually find more in use in specific data formats versus general files on a computer system, on a computing system. So yeah, so here I'm listing just kind of some of the basic commands and flags that you'll encounter when you're using gzip for the first time. So this cfar10 python.tar.gz file, right, is a compressed archive file, which I'll talk about in the next slide. But essentially, any file that you see with a .gz is a gzip compressed file, right? And so if you want to decompress that file, you can either run gzip-d, or there's always usually an equivalent sort of alias command like g-unzip. So most of the compression tools, there's always a set of these alias tools if you prefer to run g-unzip or gzip-d-d, it's the same thing. It's just decompress this file, right? So by default, all these tools are usually just the name of the tool, the command line the command line tool name, and then the input is just the name of the file that you want to compress, right? By default, some of these tools will throw away the original file, so there's options to say -k for keep the file. So if I run the decompression algorithm on this MATLAB tar.gz file and then this binary.tar.gz file, right, it'll keep those original compressed versions around and provide the decompressed versions side by side. There's also usually with each of these types of compression tools a way to control the level or speed of the compression, right? So usually if you want to the algorithm to try to compress the file further, it usually takes longer. So that's why in this gzip tool here, there's a fast and a best flag, but it's just kind of a, how much compression ratio you want to apply. And this will vary depending on the types of files that you're compressing, the data that's contained within them, and their format. So, but there is one format that is important that if you're not familiar with, that is hopefully very obvious on some of these examples. This, if .gz is an extension for a gzip file, this .tar file that I'm compressing here in this second example is what's known as an archive file, right? So most of these compression tools that you'll encounter operate only on single files, right? So you need an additional type of tool to bundle if you want to compress a collection of files, right? And so this tar command is the one that is most commonly used in a Linux environment on an HPC system, or I'm sure tar is available on macOS, I'm guessing too. But if you have a data set that is a collection of many different files and you want to package them together before you're transferring that data, right? tar is the command line tool that you want to learn how to use. So in addition to wget, gzip, tar is probably one of the most common tools that I use in my day-to-day work, right? And so let's see, what else do we want to talk about here? So yeah. Oh yeah. So the just in terms of terminology, you'll often hear people refer to tar files as tar balls. And so it's just like a ball of files that you've collected together and usually compressed. So usually you'll find, any file that's a collection of files is usually a tar file with some sort of compression applied. So .tar compression format, right? So that's colloquial referred to as a tarball. So that you'll see that terminology out there. Let's see, is there anything? So one thing that's good to know about tar is, if you learn how to use tar, right, it has, simple flags to just take, say, a directory with a bunch of files, tar it up into a tar file, and then compress it with one of the standard compression tools, right? So for example, this second to last example shows me creating -c, a tarball with gzip compression, and the -f is just for the file name, essentially. So, these combinations of flags applied to the tar one will not only create a tarball of all the collection of files that you want to put together, it will also allow you to compress it with the standard tools that you'll see. So here I included at the end just the bzip2 option. So it goes from Z to J. Mostly just because this is probably the second most common compression format you'll see. It uses a different type of lossless compression algorithm, but it achieves higher compression ratios. So if you really do want to try to shrink your data, the bzip2 format is likely the one that you'll see most commonly out there, in addition to gzip. Yeah, I don't think I'm running a little short on time, so I don't want to spend too much time here. But those are the two major ones that you'll see out there on the internet when you're downloading files or want to use it your own. So gzip is kind of a nice balance between speed and compression, where zip files here are usually take longer to compress for that higher compression ratio. There are tools, and I'll try to go through these slides here, that run compression in parallel, so you can speed up the time it takes to compress the data that you have. So if you have large files, large tarballs that you want to create and compress, you definitely should look into some of these parallel implementations. This PigZ one is the gzip, the most common gzip parallel implementation I see out there. I don't use it a ton myself, but I also don't spend a lot of time compressing a bunch of files myself. But this one is still in pretty active development, and we definitely have it available on our system in Expanse. So if you need a compression tool with to compress large amounts of data into large, say, tarballs, this is the one that I would probably look at. There is a bzip2 one that's available. It's supposed to be pretty nice. I haven't used it much myself. And the last major release was in 2014. So that kind of thing always worries me a little bit, but it's still in use as far as I can do. I could tell when doing research for this talk. But I include it here mostly for just a reference that there are parallel versions of the bzip2 format as well. So, and there is a nifty option in tar where you can actually feed it a compressor command, essentially, right? So, there's no native parallel, this lbzip2 implementation or flag for the tar command, but you can actually feed it just a command that runs that lbzip2 on, say, 4 cores or 4 threads, and will compress this directory here into the tarball you want. So just a nice little trick there for tar. So yeah, all of these tools have many, many options, and I encourage you to, if one of them sounds like something that you want to use, please do investigate further on all the options that might be available. If you don't see something that I'm covering here, this is all very high level, basic examples of commands that you can run to, for the basic functionality of each tool. Okay, so we have about 15 minutes left. I'm going to try to move through this data storage and file systems section a little bit quickly. This is going to be covered. This topic will be covered much more in depth in the second data management talk in this series. But I just wanted to provide a high-level overview of few things to keep in mind when you're transferring data between systems and when you're interacting with certain types of data storage and file systems that might affect what your data transfer sort of workflow looks like. And the most important thing is usually what type of file system are you moving the data off of to what type of file system are you moving it to? Just because in any given data transfer, obviously, you need to decide where is the data coming from and where is it going to, right? And there's different places that you put different types of data depending on how much data you have, and so forth. Okay, so I'm going to skip this. So file system, right, is how we organize with the operating system access to the data that we are talking about transferring, right? But the key concept, the key concept I want to point out here about file systems is there are many different types of file systems, but there are 2 sort of major classes that you will encounter on any given system. The one that you're, more familiar with, working, say, on your personal laptop or desktop, is local file systems. So these are the file systems that your operating system uses to organize the data on your hard drive, in your laptop, your desktop that you're using on your computer. And these are called local because they're local to the the storage device that's attached to the computer that you're working on, right? Whereas distributed file systems are what you will encounter on many of these advanced resources like Expanse, where you have actually many different types of storage systems, file systems that are not local to the given machine that you're actually interacting with, right? There are different protocols and ways that the file systems can be distributed across multiple machines, right? Over the network, right? And in general, anytime you're transferring data to an HPC system, you're likely, if your destination or source is an HPC system, the data is likely coming from one of these distributed file systems, and which type of file system you're interacting with, right, will dictate, usually the capabilities, how much storage space you have there, and even the type of file transfer mechanisms that you have sort of access to even. Anyway, so I'm going to skip this. This is just the most common default local file system you'll see on a Linux operating system today is this X4. Don't need to cover this too much. The ones that I wanted to point out are more these distributed file systems, like the network file system. So this is a way to mount storage from a server onto a client system. So, for example, all HPC systems have what are usually called login nodes, where you first interact with the system, right? And when you log into a login node, you're usually dropped into your home directory on the system. However, that home directory, you'll usually notice, is available across any node on an HPC system like Expanse, right? And that's because it's using a distributed file system like NFS is usually the most common one that I think I see used for home directories on supercomputers, right? So this is not usually a high performance file system, but it's good for providing small amounts of storage for home directories, so you can store like any software you need to install, source code, essential data for input and output for any simulations or data analysis that you're running on the system. So it's not usually where you'll transfer large amounts of data. And so the technique, the data transfer tools that are not targeting large data sets, we'll talk about here in a second, are perfectly fine to use with targeting a network file system. You have, in addition to, sort of standard NFS types of file systems, you also have what are known as parallel file systems. Lustre is one of them. These are file systems specifically designed for really high performance IO throughput. And so this, in this case, Lustre, I would say, is really more designed for like simulation workloads. So if you're dumping out large files regularly, say doing a weather simulation or something like that, that's what it's really good at handling, right? But this is also usually where most HPC systems have a large amount of storage. It's usually not backed up because when you have petabytes of data, you don't have the money to also buy another file system to back up that instead of 10 petabytes of data or whatever you might have. But it's usually one of the common sort of targets of where you'll transfer large amounts of data, because that's where HPC centers like SDSC will provide you the most amount of storage, right? Because the home directory servers are kind of small and meant to be limited in scope, where these large distributed file systems are designed for dumping large amounts of data on and storing them, at least temporarily, for your use. Another common file system you'll see in use more so these days, associated with HPC centers and supercomputers, is the Ceph file system. It allows you to set up many different types of file systems and storage. It actually has object-based storage, so similar to what is offered in sort of cloud object storage systems, which is a completely different type of interaction than interacting with file systems when you're on the command line. But this file system is usually or this storage system is usually really good at data replication and fault tolerance and high availability. So it's good for preserving your data. So it's usually used for like project type storage, where if you need to keep data for long amounts of time and make sure it's not corrupted, this is one of these file systems that you might want to target your data transfers to or from, depending on your use case for your research workflow. Okay. And there's a whole host, a zoo of file systems that I won't talk about here that you might run into. But in general, there's lots of distributed file systems out there, and each one has their own unique characteristics and sort of features that they're trying to promote. But so there's lots to learn if you run into many different file systems on different pieces, which can affect again where your data transfer is going. Okay, so of course, with the last 5 minutes, let's talk about the basic tools that you want to get familiar with when you start transferring data. So we've covered, how to download data. We've talked about how to verify that the data, is intact after download or in general transfer, right? So when you transfer your data, you can use checksums to then verify that the data was transferred, uploaded, or downloaded to the place you wanted to be was correctly done. Compression, right, is important to do before transferring data. So now we're finally at the data transfer tools. Now, let's see. I'm going to cover the first 4 here in the last 5 minutes we have. So if you're not familiar with transferring data between your local system and a remote system, or between remote systems, sort of 2 remote computers out on the internet, SCP is usually your first command line tool that you'll encounter using, right? So this is just like the copy commands on your local system, copying files between directories. This allows you to copy files between systems, right? So here I have my CFAR Python data set tarball that I want to securely copy between my local system, my laptop here, and the Oasis data mover that's available to put that file on Expanse at SDSC, right? And so I'm actually changing the name of the file too. Anyway, so this is, it's a way to remotely copy files between systems. You can also recursively copy directories. You can also transfer files or directories not between your local system and a remote system, but between 2 remote systems, as I'm showing here, all using SSH as sort of the security protocol and way to authenticate between systems. If you're not familiar with that, we can definitely talk about that in the Q&A. And there's even, fancy different flags where you can then turn on compression. So it'll actually do compression, say, of all the files in here before they transfer, so you can save space. It's one of the most common tools that's available. I mean, it'll be available on any, like all the tools I talked about today are available on any system. Should be easy to use, hopefully, once you get started. But this is to transfer, limited amounts of data. This is like your go-to first tool. The next tool is SFTP. And the only difference that I'll say here, and just to save on time, is essentially it can do everything that SCP does, but it does it interactively and allows you to actually interact with the file systems on each end if you need to. So this is a tool that you would want to use if you don't know exactly where the file is that you want to transfer. You want to poke around on the HPC system and figure out, like, oh, where did I put that file? You can actually log in through SFTP, have access to, the directory structure that's available on the remote system, find that file, do a download of that file, or you can upload the file from your local system to the remote system. And the key commands here are the get and put. So here, this is a get this file from the remote system that I've logged into, versus putting a file, uploading the file here that I want to put on the remote system, say from my laptop. So there's all sorts of commands to explore the local file system versus the remote file system. You can even change permissions. So if you need something that's a little bit more interactive on the command line, this is the tool you're looking for. Okay. Now, this tool rsync is one that I haven't used a ton myself until recently. But I would say it's once you learn SCP and SFTP, this is the next tool you really want to learn. This is the one, it's kind of like the command line Linux Dropbox for you for transferring data between your local system and the HPC system you have access to sort of maintain synchronized directories or sets of files between each system, right? So if you want to have the data set on your laptop on HPC system 1, HPC system 2, you can use rsync to regularly make sure that all of those files and directories are the same, which is pretty cool, right? So it's like a kind of like a secure copy superpower, essentially, right? And so it allows you to sort of easily back things up from one system to another or maintain a consistent set of directories and files across all these systems that you might be working with. So this is definitely one that you would want to use. And it's got all the nice features, like it'll resume, the synchronization process, depending on only which files have changed. It'll only update the ones that it knows has changed and not update the ones that have not. So it saves on the bandwidth and the network resources and transferring the data between each of these systems. So it's definitely one to check into once you start transferring data. And the last one, which I'll stop here, since I'm 1 minute over, is Globus. So Globus is probably the most common parallel data transfer tool that you'll find for transferring large data sets between HPC centers and, say, university clusters. So most universities and HPC centers will have a Globus endpoint, is what they're called, or now they call them, well, they changed the terminology recently, but essentially there's different endpoints that can point to different storage systems and file systems on each end. And Globus essentially schedules and manages the data transfer. And they even have nice web applications that I'm showing here where you can log into, say, the Expanse Lustre file system, go to your data set directory, click on that directory, and start a transfer to another HPC system across the country and just let it all happen in the background. And this allows it, it's secure, it's fast because it does it with multiple streams. So we talked about a little bit about, how to parallelize transfers. This is, the go-to if you have large sets of data that needs to be transferred quickly and in parallel across like research networks where you have these endpoints available. This is the tool you want to use. And there's a command line tool that you can install and use. There's obviously the web application here. There's even software development kits, so you can even include like I think if you're writing like some sort of Python code or working with some Python scripts, there might even be ways to call Globus from within your Python script. It's a really cool data transfer tool that's widely available to you across the research computing community. So if you're not familiar with it, this is definitely sort of the most advanced tool that you want to look into once you get started with data transfers. And with that, I will stop there since we're over time and go to the Q&A.